Hi, this is Clinton Miller, teaching AI. So we're going to begin with a binary AI model. And what this is an artificial intelligence that's able to create yes/no outputs. And what we're looking at on our screen is exactly that. It's able to create yes/no or benign or malignant outputs based off of this extensive data set that's being provided by that Excel sheet. So we'll begin by downloading the Excel sheet from the link in the description. You can get that from my GitHub, and we'll familiarize ourselves with that real quick. So after you've downloaded it and opened it, we can look at it and we'll say diagnosis in the column A. Now this is going to have ones and zeros representing benign for 0 and malignant for 1. Malignant means they're going to need to operate and it's a dangerous tumor. Now, all of this data here is the measurements of the tumor. So you've got, things like radius mean, texture mean, all of this stuff, which would be really hard for a human to keep track of this amount of data. So again, it's split up into diagnosis and the data of the tumor itself. So to start our project for real, we're going to go to colab.research.google.com. And to blow that up for you so it's a lot easier to see, it's colab.research.google.com. All right. So you'll be greeted with a page much like this, and in the upper right-hand corner, you can sign in with your Google account, and that makes this entire process free. So on the left-hand side, we'll click Folder, Upload, select that cancer.csv file, and as that gets brought in, you'll see us get connected to a runtime. So we're going to use all of Google's resources instead of our own. And then in the center, you'll see a bar where you can click into and your cursor will appear. This is what's called a cell. Now, we're going to be splitting our AI's data code into different cells, and that's going to make troubleshooting a lot easier because you can do it one step at a time. Now, as we go through our slides in the future of this video, you're going to see each one of those slides is going to be its own cell. So as we move on through the slides, we're going to go on to a new cell. Now to create a new cell, if you click into that line and hit Shift Enter, it'll create a new cell for you. Now if you wanted to test the code, you can click that play to run the cell. All right, so let's get into our slides. So again, at colab.research.google.com, we're going to be using that data set. And in our first cell, we're going to be calling in our libraries. Now, these libraries or modules are going to be compilations of code that we can call upon either entirely or as just a section of it, much like checking out a book from a library or checking out just like a paragraph you needed for a project. So we're going to be working with pandas, NumPy, and TensorFlow. Now we're going to, and sklearn, but that's a special thing I'll get into in a second. So pandas we're going to be using for its ability to read and store data in a searchable format. NumPy we're going to be using to process all these different numbers and keep them correlated to their values. TensorFlow we're going to be used for its for its ability to build, train, and evaluate the machine learning module. It's one of the most important because that's what's going to help create our brain. Now, from the sklearn, you notice we're going to a very specific part of sklearn. It's model selection. So it's a lot like going to a library using the Dewey Decimal System to find this specific book and then getting this specific chapter that we want. And in this case, the chapter we want is the train test split. Now, the train test split function we're going to be using later, and that's going to be able to split our data into training data and testing data. So if we've put all of these into the cell, import pandas as PD. This PD, NP, and TF, these are variables that we're going to use to make it easier to call on these libraries. And you'll see how they're used as we go forward. So if we've got this put into our first cell, you can hit Shift Enter, and it'll check for any errors. You should see a green check mark, and we can move on to the next one. So in the next cell, we're going to be using that data set, calling it in using pandas, but using that variable PD to call on it, so it's a lot quicker and easier. And we're going to use its function to read in the cancer.csv Excel sheet and store the data in a searchable format. We'll then create variables. The X variable will make that equal to all of the columns in the Excel sheet except the diagnosis column. And you can see that with the dataset.drop, which means we're going to drop everything that is included in that parentheses. So it's just the diagnosis. So it's a lot like if we just cut this whole diagnosis column out and we kept everything else. So all this data is going to be equal to X. And then with Y, it's the inverse. We're going to make it only equal to that diagnosis column. So we've now split the data into two separate pieces, the Y data and the X data. Now we'll hit Shift Enter and go to our next cell. Again, if you see a green check mark, everything's good. If you see a red X, just refer back to the previous slide and make sure there's no typos or anything like that. So in our next cell, we're going to be splitting our data even further. So we've already split it into Y and X. Now we're going to split Y and X into training and test data with that function that we got from sklearn. So using that train test split right here, using that train test split function, we're going to split the X and Y variables into test sizes of 20%. And to give a picture, essentially, we have right here our data, and Y is going to be split 20%, and X is going to be split into 20%, and those are going to be our testing data. So our AI will look at that as if it's brand new data it's never seen, and it's not going to be involved in its training, so it'll be as if we were uploading new tumor data from new scans that we were running on the patient. All right, so Shift Enter again, and we'll be in our next cell. This cell is one of the most important because here we're going to actually build and train the model's brain. So we use a sequential model because our layers need to be added and processed in order. Next, we define the layers of our model, which is where all the processing will happen. And each line will add one layer to the model. So you'll notice that they all begin with model.add tf keras layers dense, which means that we're going to be importing dense layers. So the dense 256 section adds a layer with 256 nodes. The input shape ensures that the layers use all data points from the X-train, so all of our X-training data. And the activation sigmoid applies the sigmoid function, which crunches things down to put out only a 1 or a 0, so binary outputs. That's going to go on from each layer to each layer until it finally gets to where it only has one node. Then that final node is going to be pumping out our actual output from each equation. So here, and then we have our optimizer. So that final output we created in our final layer is going to be pushed to the optimizer, and then that is going to split the results into computed guesses and actual values, optimizing the model's accuracy. Now, we want to give it a metric to optimize for, so we gave it accuracy because we want it to be as accurate as possible. I know that's a lot, but here's a picture to help make it simpler. So in a dense layer, we created 256 nodes. Each node draws input from each data point of X trained, so the training data of X. Each node will formulate a guess based on the sigmoid activation, again, crunching it down to just a 1 or a 0 output. It's either yes or no, benign or malignant. So in this picture, you're seeing like all this X-train data being compressed and pushed into the layer node, which is going to grab the data and give it shape. It'll be passed to layer node 2, where the shape data is processed and passed to processing nodes. Then finally to that layer 3, where there's only the single node to give it a final output. And again, that sigmoid activation is going to squash that data down to a final yes or no. And this is going to happen across 256 of these nodes. So it's a lot happening at once. Now we're going to since we've defined the layers, we'll compile the module. Now we're not in the next cell. I just had to split these slides up because it's a lot of code. So in that same cell, we're going to do the model.compile parentheses optimizer, and we're going to type all this out. And once you run that, we've compiled the model, we've given it the optimizer atom, and that's going to adapt the learning rate to make it quicker each time. It's going to learn more refined variable equations. It's a lot of complex math, but it all happens in the background, so it makes it a lot easier for us. And it's going to keep optimizing to create more and more accurate results, and that's its intent. And again, here's a picture that's going to help break that down. So again, that final layer guess, where there's only one node, is going to be passed to the atom optimizer. The optimizer is going to check that against the actual answer, which we've stored in that Y data set. So all these diagnoses, it's going to check, make sure that these measurements equal that, and if it's right or wrong, that's all going to be passed down to the model confidence, which is going to be building what the model says is its best guess, using the best algorithm to create the best answer, the most accurate answer. Now we'll hit Shift Enter, and we'll go down to a new cell. In this next cell, we're going to do this loss accuracy equals model.evaluate x underscore test, comma y underscore test. And what we're doing here, loss accuracy defines the variables that store the results from the evaluation. So all of that processing that went on above it is going to get stored into this accuracy based on loss. We make that loss accuracy variable equivalent to the model evaluation. Again, all that processing that was done higher. So that function is going to test the model on the test data set, the x test and y test, and return the loss and accuracy. So how much of it was wrong, how much of it was accurate, which equation had the best, and which one of those were in common. So which piece of the equation was common between the previous ones. Finally, it's going to print the result, which is going to be the accuracy on the test set, which again, the test set is all of the data that it was kept hidden from. So this is like if we were loading in brand new statistics. And then it's going to go on to the next cell. So Shift Enter, check for errors. And in this next cell, what we're doing here is we're calling on that NumPy to give it an array of numbers from that Excel sheet. And this is the same process that would happen if we hook this AI up to the actual scanner um, medical device that's creating all of these dimensions of the tumor. And if it was loaded right into our AI, this is where it would go. So I've manually entered these variables here from a separate cell that I removed from the sheet. So this is 100% brand new to the AI. So we enter it as new tumor data. And that NumPy array is going to contain data on the tumor dimensions. Each value represents a different feature or measurement related to the tumor. The model.predict that you'll see in the next line is going to guide what our AI model is predicting. And in this case, we're using the trained model to make a prediction based on the above line new tumor data. And then finally, we create a print for it to tell us exactly what its new prediction is. So if we Shift Enter, let that go, it's going to show our next cell, which this is where we're creating the parameters for its final test. Now, its final test is going to have a threshold of 0.5, which means 50%. So if it's above 50%, it's malignant. If it's below 50%, it's going to be benign. Now, our accuracy rating, this way it tells us exactly what it believes its accuracy rating to be based off of all of its training, and it stores the accuracy of the model from those previous layers of the brain. And then finally gives us a diagnosis based off of all of its equation and complex math, what it believes is the malignant or benign. And finally, it will predict, give us that printed prediction of its benign, malignant, the accuracy, and its confidence in that. Now that's the end of the slide, so pretty straightforward how to make it. And when it's finished, it'll look something like this. Now we'll zoom in so we can go cell by cell. And again, we'll hit play, looking like it's all green. See how it goes cell or line by line within the cell? You're able to check that. You can load the data set. Oh, it's not going to like that because I didn't load the data set. So here we go. We'll load that data set, make it happy, run it again, green check mark. That's what we like to see. Then we split the data set into training and tests. Boom. Now we'll build that model. Now you see how we have this 1,000 epochs? That epoch is equivalent to a training session. So while this is running, I'll give you kind of a brief on what's happening here. So we created each layer to have 256 nodes, and we gave it 1,000 epochs. So essentially it's going through 256,000 squared variations of the equation to find the most accurate. And you can see on this right-hand side, the accuracy rating of each one of these different equations and combinations of information that it's going through. And you see it fluctuates. It goes 96, 94, 89. It's going to pick the highest one possible, and that's what it's going to store as its actual algorithm for testing new data. So this will keep going, and it's at 600, so it'll keep going for a while. You can show or hide this. Once it's finished, it'll have the highest accuracy possible. Wow, there was a 100%. Sounds like the AI was cheating there. And 800. You'll need to do this on your model as well so it actually trains. So every time you run this, it's going to try to go through the 1,000 epochs each time. And you can play with the number of epochs as well. If you want to do more to get it more accurate or less, then that's fine too. But just understand that there is such a thing as overtraining. So if you set the epochs too high, you'll see that it trains really well and will give you 100% accuracy in the training. But then when you go to actually test something, somehow the accuracy has fallen off. That's because the AI has trained itself so well, it's able to predict its own answers in the training sessions, and it's going to screw up when it's using new data it's never seen before. So go ahead and play with those kinds of variables and see how different the AI model works. All right, it looks like we finished our 1,000 epochs. It's going through and checking for errors. We can go ahead and stop that one and go on to the next line. Here again, it's going to evaluate itself. And then this is our new tumor data that we put in with all of those preset variables. And it gives a prediction for the new tumor data at 0.0023. So what does that mean? Well, that's why we created this threshold. So as we go and play this, there we go. That's why it's important to play all of the codes in sequence and make sure you get those green check marks. You'll see that based off of all of this that we put into this cell, the predicted diagnosis is benign with an accuracy of 93%. Now you'll notice in the beginning of the video, it had 97%, and that is what we're talking about with the training. Because I've run it through almost 2,000 of these, because I've run it twice, it's starting to become less accurate in the actual test. So that is building a binary AI model. Feel free to play with the equations and variables, and be sure to look in the description for links to NumPy, Pandas, and TensorFlow and sklearn. All of those links are going to lead you to those home pages so you can read up on those different modules and where you may want to use them in the future. Thank you and have a great day.